Hi, and welcome to this webinar for PACSystems SafetyNet. My name is Steve Ward, and I'm a subject matter expert on process safety systems working for Emerson. Our controls and software portfolio includes PACSystems PLCs, Movicon HMI SCADA, and PACEdge Industrial Internet of Things. In this session, we're going to be focusing on process safety, but we also have all of these other controller and other offerings, and process safety is an extension to these existing components and can be used alongside them as well as independently. So why do we need process safety? Well, there's a saying in the industry, if you think safety is expensive, wait until you have an accident. That's attributed to Trevor Kletz. Examples of very serious incidents include the Piper Alpha platform. An explosion on the 6th of July in 1988 killed 167 workers and destroyed an oil rig. This affected 10% of UK oil production at the time and led to financial losses of 1.7 billion in UK pounds, and that would be the equivalent of over 4.5 billion pounds today. Another example is the Texas City refinery explosion on 23rd of March 2005, which killed 15 workers, injured 180 others, and severely damaged the refinery, leading to financial losses of over 2 billion. What we're also not counting here is potential damage to the environment, which often can't be counted. So there are very serious implications in not mitigating safety and then potentially causing huge consequences to the people involved, both to the businesses and to the individuals and to the environment. So safety is very important to prevent these sorts of incidents from occurring. So in the safety hierarchy, there are multiple levels of protection. We start with normal behavior, which is the day-to-day operation of a process control system. And within that, there may be process alarms. When an operator needs to intervene in the system, there would be a standard process for shutting down the system called process shutdown, and that may also lead to trip alarms. Where events go beyond normal operation is when we get into the safety instrumented system stage, and that's where an emergency shutdown is required. So these are preventative measures. Above this, then we have mitigating measures, which are when something has actually gone wrong and we're trying to prevent further serious damage or injury. So for example, is active protection, such as relief valves and rupture discs. We can also have passive protection. That might involve physical segregation of a process plant. It might involve dikes, which can capture leaking oil, and there may be other mitigating factors there. And the final emergency response mitigating factor, that's what happens at the plant and the emergency response level, including things like evacuation and then potentially calling in third parties like the fire authorities who could maybe put out a fire or deal with whatever the event is. So there's a big hierarchy there. Where we're really concerned with what we can offer with PACSystems SafetyNet is in the yellow box there, which is the safety instrumented system. So a safety instrumented system is a electrical or electronic or programmable electronic safety related system, and it's made up of the sensor or the input. That can be switches or sensors or signals or other sorts of detectors. We have a logic solver, which is the PLC with its CPU and microprocessor, and then there will be a final element or an output, which could be a valve or a pump. Now there are standards that covers these. In general, IEC 61508, that's the standard that covers the hardware, but there's another standard called IEC 61511 or 61511 that covers the entire system. So if you look at a typical system, a transmitter could be a valve. The logic solver would be the safety instrumented system that's actually doing the control of that valve and reading the valve, and then controlling the shutdown of the system when events go outside their normal operating process. And we can also think of that as a sensor feeding data into the logic solver and then controlling the output. So there are practical implications which are caused by the safety standards and by various laws. So for example, in the UK, we have the Health and Safety at Work Act, and that includes various implications. So some of these are maybe not so obvious, some of them are a bit more obvious, But the first one I've got here is that it's not down to the vendor to propose a safety solution. So we are the vendor. Although we can provide a safety solution, it's not up to us to tell the end user what they need to implement. It's the other way around. The end user has to tell us what they need, and then the advice we can give them is to provide a safety solution that is still capable based on what the end user is telling us. Safety extends beyond the control system. It's not just a safety system, but there may be signage, there may be personal protective equipment, there may be training, there may be specific people who have assigned safety responsibilities. Of course, there are the sensors and actuators, some of the passive safety that we saw in the previous slide, and there may be many more. But ultimately, under law, the end user remains responsible for safety, and they must ensure that what they implement meets their requirements according to the functional safety assessment that they perform. So these are the requirements of the end user. They must employ safety personnel, and those personnel must perform a functional safety assessment. The safety personnel must ensure that systems are installed and operated in a safe manner. And there must be documentation around the safety system and safety overall, including competence management, that's where the training part comes in, and documentation of all the applications requiring safety. As I mentioned, the vendor can only offer very limited guidance on safety. So as Emerson, we may be able to provide advice, and certainly we can provide technical details around what PACSystems SafetyNet can offer, but we aren't actually qualified to tell the user what they can do and what they need. Now, you can become qualified. It is possible to become a safety specialist. You have to be trained and approved. For example, there's a TUV 3-day training course followed by, I think it's a 4-hour exam, and that needs renewing every few years. So you could go through that process to be a qualified safety expert. And then you also need to follow all of the appropriate safety standards around whatever industry is you're working in. Another point here that a lot of people get confused about, redundancy is not the same as safety. You can have a safety system that is redundant, but you can also have a safety system that is operating in simplex mode. The safety comes from the design and qualification of the system itself, not just from having redundant components. And the opposite is also true. Just because you've got a redundant system, it doesn't mean it's a safer system. It might give you higher availability and it might be more reliable in operation. But if it fails, it might fail to the wrong state, leading to a non-safe situation. So redundancy is not the same as safety, and vice versa. Let's compare machine safety versus process safety. So machine safety is covered under the EN ISO 13849 standard, along with other standards. And generally machine safety is focused around protecting the operator from harm. So typically this is focused on high demand or continuous failures under operator safety, where the safety operates frequently. So for example, imagine that you have an operator that's loading a machine with components. The machine then performs an operation, and then the operator unloads those components. So that might be happening every few minutes or even every few seconds. So each time the operator puts their hand in the machine needs to be in the safe state to prevent operation and leading to potential crush injuries. So that's one aspect of that machine safety. Typically with machine safety, the safe state is off or stopped so that nothing can operate to cause injury or anything else. Normally equipment availability in this case is not a concern. The machine reset time is usually fast, and the system is only shut down or stopped for as long as the operator is performing the action to which they might be exposed to danger. Generally these are discrete safety signals, so either on or off, and typical examples include press brake safety guards, assembly cell keep out zone to keep people away from the dangerous areas, robot cells, you have guarding around the robot cell, and there may be safety guards against automated crane equipment. Process safety is quite different. It's focused on low demand failures, and the focus is not just on the operator, but it's also on the asset or the equipment, and also on environmental safety. Now, unlike machine safety, with a process safety system, ideally it will never operate. If you have an issue where the process safety trips the plant or shuts down the plant, something has gone seriously wrong. There's been an oil leak or a gas leak or something else has happened. So you can think of it a bit like an insurance policy, but you need that safety just in case. Now, with process safety, the safe state is usually off. So, for example, with emergency shutdown, you normally want to close a valve and stop operation of the plant, but it can also be on. If you've got a fire and gas system, you might want to open the valve to deluge the plant with halon or whatever the extinguishing material is. So, safe state can be off or on. Equipment availability can be a concern. Because process reset times can be long, you ideally want a process safety system that's also reliable. If a safety system trips, then that's not an issue from a safety point of view because the system is safe. But if you're running an oil refinery that is very expensive and needs to run 24/7, then you don't want it tripping spuriously. Instead, you have a more reliable system with higher levels of availability so that you don't have to worry about shutting the system down. And again, there's a difference there. Process reset time can be very long. If you shut a process down, it can be several hours or even days in order to restart the process back to where it was running and getting into its normal operating state. So avoiding spurious trips is important, but that's outside the scope of the safety system. That's an availability concern. Now, with process safety, we often find a mix of discrete and analog safety signals. And example applications include things like burner management systems, emergency shutdown or ESD, high integrity pressure systems, and fire and gas detection and mitigation or F&G type systems. Let's do a brief comparison of functional safety standards. Functional safety is achieved when the safety functions of a safety related system can satisfy their required safety performance. So functional safety is normally undertaken by active systems, but as we've seen before, you can also have additional safety that can be implemented by passive means. So the primary standard is IEC 61508. This is the overall standard, but this can't actually be implemented. You have to use one of these other underlying standards. So typically the vendor would certify their hardware to IEC 61508, but the user has to certify their machine or process to one of these other standards. So for machine safety, we've got ISO 13849, which gives us an ISO functional safety standard related to performance levels. So you might hear of things like PLD, so that's performance level D, which is a particular level of safety. There's also the related IEC 62061, which is an IEC functional safety standard, and that uses safety integrity levels. So you might see SIL 2 or SIL 3. For process safety, the standard we use is IEC 61511, and that's a process safety standard which uses safety integrity levels. But it's important to note that although we've got two different standards here, both implementing safety integrity levels, the way we calculate those safety integrity levels and the actual standards and how they apply might be different in each case. So just because you've got something that's safe under machine safety standards doesn't mean it's safe under process safety standards or vice versa. They are different standards and they need to be applied differently. So the standards generally define a risk reduction level for a given application. And the idea is that each increase in level, so for example, if you go from PLD to PLE, or if you go from SIL 2 to SIL 3, each increase in level corresponds to an order of magnitude in risk reduction factor, or RRF. Now, some of the calculations for this get very, very complex. You need to look at things like probability to failure to danger. You need to look at the amount of failures that can actually be detected. You need to look at if there's failures which can affect the system leading to harmful impacts or failures which don't lead to harmful impacts. And there are a lot of calculations involved here. But generally, if we have something like SIL 1, SIL 1 means that there are additional measures in place to reduce the probability of a dangerous situation by 10 times. If we go up to SIL 2, that's reduced by 100 times. If we go up to SIL 3, it's reduced by 1,000 times. And if ever you get to something like a SIL 4 system, now we're looking at a 10,000 times reduction. The idea is, these risk reductions, these correspond to the likelihood and severity of a failure. Higher risk means greater SIL and vice versa, although that's not always necessarily a good thing. Higher SIL does cost more money, and it might also lead to operational issues, including the simple fact of getting insurance for your application. If you've got an insurer who's looking at something that's rated as SIL 2, then that's okay, that's a reasonable level of safety. When you go up to SIL 3, then that normally implies that it's much more dangerous and you've had to do a lot more work around making it safe, which also implies that if anything did go wrong, then it would be a lot more dangerous. So there would be cost to the environment, cost to the people, and so on. So higher SIL isn't necessarily better than lower SIL. And this is where the functional safety assessment has to be performed to determine what SIL level is required. What I've seen is a lot of people have moved from SIL 3 to SIL 2 by adopting mitigating factors. So for example, if you've got an oil rig, if it's a manned oil rig, then you might find that you need SIL 3 reduction because you've got to protect all those operators. If you can move to unmanned operations, now you don't have any people or as many people to worry about, so you might be able to move down to SIL 2. So that's a good example of how you can reduce the risk factor by removing people from the equation and then reducing the amount of safety you require. I also hear of other trends though, where people are looking to reduce to things like maintenance operations. So for example, one way you might get down from SIL 3 to SIL 2 is by having more regular inspections, but because it's an unmanned operation, that means you have to shut the plant down while you're performing the inspection. So that affects your availability. So some people are looking to increase from SIL 2 to SIL 3 because they want to reduce the amount of time the plant is down. So that means they have to work for longer between the different operations where no one is present. So there's different standards and there's different requirements that apply, and different users will have different ideas of what they need. But again, they have to decide what level of functional safety they need, and that needs to be based on a defined methodology, typically by performing this functional safety assessment. So here's an analysis of safety integrity levels in the process industry. Generally, we find that about 51% of applications are SIL 1, so that's by far the majority of them. About 32% are SIL 2, 3% are SIL 3, only about 1% are SIL 4, and then there's also some applications where no SIL is required, where there's no safety. So if there's no SIL, you could use any application. A standard PLC system would be fine. For SIL 1 or SIL 2, normally you would use a similar level of control system, but the difference would be in the amount of testing and the amount of performance levels and the amount of additional calculations and the amount of additional mitigation factors you might need to perform. So I would often say SIL 2 and SIL 1 are very similar in terms of their requirements from the control point of view, but the documentation and procedures around it are a bit different, i.e. SIL 1 doesn't need as much work because, as we saw before, you're only looking at a 10 times risk reduction, whereas SIL 2 is 100 times risk reduction. When you get up to SIL 3, you've now got to perform a lot more mitigating factors. As I mentioned, we're now down at 1,000 times risk reduction, which means there's a correspondingly extra amount of work you need to do to make sure that that system does meet your SIL 3 requirements. SIL 4 is very rare. That can be covered under things like blowout preventers, and SIL 4 is also applicable in the nuclear industry. Just bear in mind that the nuclear industry has its own standards which aren't necessarily corresponding with the IEC 61511 or IEC 61508 standards. And SIL 4, of course, if you're talking about nuclear, then that's extremely onerous in terms of what's required. So SIL 3, bear in mind these figures come back from 2007. SIL 3 is about 8% of the market. So it's an attractive part of the market because these are quite complex systems and there's a lot of services around it, but it also requires a lot of additional work to achieve that. So this is where we are now. Emerson is introducing the PACSystems SafetyNet SIL 2 safety solution in order to get back into the safety market. We've been in the safety market before. In the 1990s, we introduced the Genius Modular Redundancy solution, which could meet SIL 2 or SIL 3, and that was based on Series 9070 PLCs with Genius I/O, and they were configured together with a variety of additional techniques and methodologies to allow us to do voting and to make the system more safe. And they were approved to SIL 2 or SIL 3 by TUV under IEC 61508. 1990s was a long time ago. That hardware is now all discontinued and no longer available. In the meantime, we did introduce a product called SafetyNet, which is something we acquired from MTL with their most technologies. SafetyNet is based on the PAC 8000 controller, but again, that was obsolete since 2017. And since then, we haven't really had a good safety solution. So we're now re-entering the safety market. We can see there's sufficient demand for, certainly for SIL2 systems and SIL1 as we've seen. So we're introducing the PACSystems SafetyNet SIL2 safety solution to go after some key targets. Key targets include modernization opportunities. There's plenty of PACSystems or SafetyNet still out there based on the PAC 8000. There's plenty of GMR systems, so we're looking at modernizing those. Major applications for that would be ESD, emergency shutdown, but there's also some fire and gas and some BMS systems. One thing we're probably not getting involved in is turbo machinery and critical process controls. We just don't have the hardware for that. Turbo machinery needs some additional speed control and speed sensing, and critical process control is harder because unlike, say, a fire and gas or ESD system where the response times are quite slow, critical process control can need high-speed control instead. Another opportunity for us is to work with our Emerson colleagues, so that includes EMSOL and Fisher, and we can leverage their relationships where we don't currently have systems running. For example, there might be a fire and gas detection system which links into a fire and gas system, and often they're requested to be SIL2 or SIL2 capable. So of course we can work with them to implement a control system working with those fire and gas detectors. We can also work with existing customers who maybe have used our systems in the past, or maybe they already have our PACSystems controls and are looking to extend out to safety. So there's a variety of existing customers we can also work with in order to provide this new safety solution. So this is the PACSystems SafetyNet safety solution. It's a process safety solution certified to IEC 61508, and it's suitable for process safety applications to SIL2, including ESD, fire and gas, burner management systems, and others. This is based on our existing PACSystems controllers and Versamax I/O ranges, and we're using our PAC Machine Edition programming and control software in order to have a lot of family commonality with existing PACSystems ranges. Now, we've gone through various processes to get this approved. We're currently working with a dual hardware arrangement. This redundant hardware allows us to have the diagnostics to be used for low demand applications and to meet the requirements for SIL2. Other benefits we have is open communications for easy integration with other applications. So our primary protocol will be OPCUA, but we also support Modbus, we support Ethernet Global Data, and potentially we can support integration with other systems using Profinet and our other standard networks. Now, product shipment is now starting. This is now open for orders, and we expect to be able to ship starting in the next few weeks. And prices and availability and documentation, that's now all confirmed. So you can see by looking at this brief architecture here, you can see we've got a safety controller or safety CPU, which is based on our existing PACSystems Edge controller. We have an Ethernet network over which we're running our Ethernet Global Data Protocol, but that's configured as a so-called black channel, which means we're controlling the impact of the safety network. The benefit of that is it means you can use any components on that safety network. They don't need to be, for example, dedicated switches. We're then using Versamax for our safety I/O, and then the I/O is duplicated, and then we use what we call field terminal assemblies or FTAs, which give us the link to the safety I/O devices. So the CPU can be simplex or redundant, but the I/O has to be redundant, and that's not for availability reasons. The reason we have the redundant I/O is for the diagnostics we need. So if any single I/O point failed, then we can detect that, and then we can decide whether we want to trip the plant or go to some other state in order to control the way the plant works. So again, the requirements of the actual plant and what's required there for the operation, that would come from your functional safety assessment. Now, normally a safety system operates independently. There may be a HMI SCADA involved so that we can have monitoring of what's going on. And note I say monitoring, it's very rare to modify the safety system. You don't modify set points, you don't change the operation of the safety system. The reason is if you were to make any changes, that would imply that your safety requirements have changed. So you'd have to redo your functional safety assessment, and you'd potentially have to retest and recertify the system in order to get your safety qualification back. So normally a safety system, once it's implemented, it's locked down and there are no changes. So you would have a HMI SCADA system, but that would be used for monitoring and diagnostics and fault detection, not for actually controlling the system and performing set points. Even something like the shutdown, that would very rarely be software defined. Normally you would do that in hardware to make sure that you've got control over the safety functions. And the reason for that is, it's pretty much impossible to certify for safety a Windows-based system. There's too much that can go wrong, so you can't prove that the system will be safe. So that's why you normally use the HMI SCADA for monitoring only. Of course, you've got the engineering workstation, which is running PAC Machine Edition. And then there's also a possibility to integrate with other systems. We do support OPC-UA, we do support Modbus, so you could integrate with a DCS. We do support EGD, so you could integrate with other control systems, and I've got some architecture showing that later on. So this is our safety controller. PACSystems SafetyNet is the brand name for the product range. PACSystems, of course, is our overarching brand for our PLC systems. SafetyNet is an existing brand name that we own, and we're choosing to call this the PACSystems SafetyNet Safety Controller, and the actual part number is the CPS 400. So you might hear people refer to it as CPS 400. So this is based on our existing Edge controller range. We've got the CPE 400 and the CPL 410. So it's actually identical hardware, but with slightly different firmware and different capabilities. And a key point there for safety, you'll notice we've got a yellow label. Now, this is a compact and powerful safety approved CPU. The initial release will handle up to 2000 I/O. In terms of memory, it's got 64 megabytes of RAM backed up with flash, and that's non-volatile memory using the energy pack. The energy pack is optional, so you don't have to use that. Again, with a lot of safety systems, because they're booting up with known parameters each time, you're not having to store any data because it's always going to start in the same way. So the energy pack would be optional, but it is available for people that might possibly be using it for additional functions besides just safety. Now we've got multiple gigabit Ethernet communications. We've got dual gigabit Ethernet on ports LAN 1 and LAN 2. And with those, we can implement the black channel for our I/O communications. So the black channel is part of the safety application. And what black channel means is you can't see inside it. It's black. We as Emerson have taken control of what that I/O is doing, and we certify it for safety use. And the idea is, people say, well, what happens if the black channel goes wrong? Well, then if the black channel communications fails, then the I/O would go to its default state, typically off, which would cause a trip of the plant. So it's a safe communications mechanism that is protected against spurious and incorrect messages, and we call it a black channel communications. It's actually based on our Ethernet Global Data Protocol, but with additional work to make it safe, and that's where the black channel part comes in. Now we also support standard EGD, which gives us the capability for peer-to-peer communications to non-safety controllers. We support OPC-UA, which would be our preferred communications protocol, because that can be secured and encrypted, but we do also support Modbus TCP as well. Again, typically with a system, there wouldn't be any writes to the system, so normally this data would be one way from the safety system to an external control system or DCS or whatever. So if you're familiar with the CPS 400 hardware and the underlying CPE 400, CPL 410, you'll notice that LAN 1 is a single port, but LAN 2 includes a switch. So you've actually got one IP address, but two ports there. LAN 3, that is used for synchronization with the redundant CPU if you have a redundant system. So that's not available for the user. And of course, those of you that are familiar with the CPE 400 and the CPL 410, you'll know there's another Ethernet port underneath for PAC Edge. Well, with the CPS 400, PAC Edge is disabled. There's no PAC Edge support at all. So that additional Ethernet port is disabled as well. So with these CPUs, they're available for DIN rail or panel mount. The part number includes both a DIN rail connector and a panel mount connector. They're all based on 24 volt DC power, and they're about 35 watts, so that's just under 2 amps roughly. Temperature rating is -40 up to +70 degrees C. And we do offer a conformal coat option. So if you're going into certain environments where there's a potential for environments where it might be salt spray or hydrogen sulfide or other corrosive environments, you can have a conformal coat option. On the CPU side, the architecture is built around either a simplex or redundant CPU. From the SIL 2 certification point of view, there's no difference, but the idea of having a redundant CPU, that gives you the capability to have slightly higher availability for the system. So with a simplex CPU, if the CPU fails, the plant trips. If you've got a redundant CPU, you've got the possibility to have one CPU fail or be turned off for maintenance, and the other CPU can carry on running the safety function. So it gives you higher availability without affecting the safety function. And it's up to the user what they want, but effectively, it's just one extra cost inside the system to be able to get that higher level of availability. So I would expect most people will go for a redundant CPU just to get that higher level of availability. Otherwise, your plant is stopping when there's a failure, and that can be extremely expensive. So the PACSystems SafetyNet I/O is based on our VersaMax I/O range. So we've taken our standard VersaMax I/O, we've enhanced it with additional firmware and additional software capabilities. We've changed the plastic color to be yellow again to certify and indicate that it is a safety system, and it's certified to the SIL 2 level in conjunction with the other PACSystems SafetyNet components. So with this, we've got what we call a safety bus interface, which is the unit on the left, which communicates with the controllers via Ethernet. There are serial ports built in, but they're generally not used. You could potentially use one of the serial ports for downloading the configuration, but it's unlikely you'd need that when everything is connected via Ethernet as well. On the I/O module side, we've got a combination of different modules. We've got a 32 channel discrete in, a 32 channel discrete out, and a 15 channel analog in. Analog outputs are not supported. If you wanted to use a system with analog outputs, then that would have to be in a separate non-safety system that could communicate via the main safety system with EGD. It's a dual I/O arrangement. You do need 2 lots of inputs and outputs, so the complete I/O stack would be duplicated. And then there is voting available. Depending on what the functional safety assessment says, you can either do 1 out of 2 or 2 out of 2 based on what the requirements of the application needs. And potentially within the application, you can do additional voting. So we do support 2 out of 3, 2 out of 4, and potentially more voting solutions as well. But 2 out of 3 and 2 out of 4, I haven't come across anything that needs more than that. But generally, again, for SIL 2 applications, normally the risk mitigation, it doesn't need to be that high. So typically it's 1 out of 2. So if any one input comes on or any one input goes off, then you trip the safety function. Or sometimes you might have to be monitoring both inputs. So you might say if 2 inputs come on or 2 inputs go off, then you perform the safety function. Same with the outputs. Again, you can either decide when one output turns on or one output turns off, then you trip the safety function, or maybe both outputs have to turn off. And again, that would depend on what your functional safety assessment says and what the application requires. Now with this one, we have the safety bus interface there with its Ethernet. It's got a single LAN port which supports 100 megabit Ethernet, again using that black channel for I/O communications. So that would be connected to the controllers. In a small application, you could potentially use a single Ethernet cable directly to the controllers. But in most applications, there would be the requirement for some sort of external switches. But because we're using black channel, they don't necessarily have to be Emerson switches. It can be any switch. So with this, mounting is DIN rail. It's 24 volt DC power again. VersaMax I/O is rated at 0 to 60 degrees C. And again, there's a conformal coat option if you are going to put these into environments where there are corrosive atmospheres. To handle the dual I/O arrangement, What we will be using is what we call field terminal assemblies, or FTAs. These are also known as splitters. That's what the certifying agency calls them. But the idea of the FTA, this is to allow the connection of the sensors and the actuators to the system. Now, in many safety systems for SIL 2, there would only be a simplex sensor and a simplex actuator. So for example, you might have a gas detector or a flame detector, and then the flame detector would go into the safety instrumented system, which would do the processing of the signal, and then there would be an output to your deluge valve or to your emergency shutdown valve, or whatever your application requires. Now, the way that PACSystems SafetyNet works is, to achieve the diagnostics, we have dual I/O. So you have two inputs and you have two outputs. So what we need to do is we need to have a way of having the simplex sensor be split out to two physical inputs, and also then on the other side, when the outputs come out of the dual output modules, they have to be ORed down or ANDed into a single output to control whatever the output device is. So that's what the field terminal assemblies do, that they do the ANDing or ORing of the inputs and the outputs in order to be able to use a dual control system, but with simplex sensors and actuators. Now, it is possible that some solutions will use duplex sensors and duplex actuators, in which case you might not need the field terminal assembly, but I would imagine at the SIL 2 level that's going to be quite rare. Normally you're only going to have a simplex sensor and actuator. There's another function that the field terminal assemblies can do as well, which is enhance the diagnostic level, including the possibility for line monitoring. So for example, on the input side, it's all very well to know that you've got 0 volts or 24 volts, but you might also want to know, are there other issues with the input? Is there a short circuit? Is there an open wire? Is there a connection, a cross connection to earth, or some other issue? And that's where these field terminal assemblies can give us additional diagnostics over and above what's available inside our standard I/O modules. So again, we have this option of voting, 1 out of 2 or 2 out of 2 for the inputs. We do support input voting in the controller, and by using more inputs beyond the standard dual input arrangement, again, you could support 2 out of 3 or 2 out of 4 by using additional inputs. I don't see much demand for that, but 1 out of 2 or 2 out of 2 would be common. On the output side, you can do 1 out of 2, which would be like an OR arrangement, or 2 out of 2, which is an AND arrangement. And in this case, the output voting is in the field terminal assembly. It is possible that if you needed higher levels, you could do 2 out of 3 at a device. There are some devices available. I remember working with some process with some particular valves where the valves could take 3 outputs and then perform the 2 out of 3 voting inside the actual valve itself. But again, that's normally for SIL 3 level applications, rarely encountered at the SIL 2 level. So the field terminal assemblies, they give you your connection of your sensors and actuators into the system and to the outputs themselves. Now, it was planned that Emerson would offer these field terminal assemblies. If you look at the Exeda certificate, this says that any SIL 2 or SIL 3 splitter can be used. And at the moment, we're planning to publish details of splitters which are available from a company called GMI International and also from MTL. So they have a variety of different splitters available with different capabilities. And our aim is that by 2026, we will have Emerson branded field terminal assemblies, which will be in our price list and available from Emerson as well. So hardware is one aspect. The other area where Emerson has done a lot of work is in supporting application development using safety function blocks. Now, it's the same PAC Machine Edition configuration programming and software as standard PAC systems. So you can use ladder logic, you can use structured text, you can use function block diagram. But what we've added is a variety of safety certified function blocks specifically intended for safety applications. And along with that, we have Emerson templates which allow you to have fast project startup. So we've got templates pre-configured for 2, 4, 6, 8 and 10 I/O drops, and they're configured with capabilities of up to 1200 AI, 2560 DI and 2560 DO. So we feel that would cover us for the vast majority of applications. Potentially we could go for more than that in future versions, but more likely users aren't going to put all their eggs in one basket, as we say. More likely it would be preferable to have multiple safety systems and they will be able to communicate with each other in the future using that black channel communications. As well as the pre-configured templates, we've also included flexible safety function blocks to simplify the application development and to control all of the flow of logic from the sensor to the actuator. So first of all, there are analog input and digital input health and voting blocks. They validate the dual inputs from the sensors. There's an AI block that allows validation of the analog signal. There's voter inputs, which can give that final input signal to the application. There's a discrete voter block, which allows for that additional voting logic, for example, 2 out of 3 or more. And then there are cause and effect input blocks, which can implement a cause and effect signal into the application. And then we have a cause and effect block, which allows you to combine all of the cause and effect input blocks to allow implementation of the actual cause and effect matrix itself to the actuators. These blocks, they include delays, they include bypass functionality, they include reset capabilities, and they include first cause recording as well to allow you to understand what was the first thing that actually went wrong and caused the trip of the plant. Now, outputs don't necessarily need to be voted inside the system. Outputs are actually voted at the field terminal assembly. So typically you'd use an AND arrangement for ESD. So both outputs have to be on. If either output goes off, then the system trips. But for fire and gas, where you want to energize a valve, normally it's the other way around. It's an or one out of the two function. So as soon as one output comes on, that's when you trip the deluge of whatever your fire and gas extinguishing is. So they're normally voted at the FTA. So all you need to do in the logic is just turn the two outputs on, and then the hardware will take the rest of it. So those flexible safety function blocks, they do considerably simplify the application development, and they give you a lot of extra capability, and they are safety approved. So that obligates the need to do a lot of testing in the application itself, because our safety function blocks provide that certified capability without you having to write the extra logic. Other safety logic may be added to the final application. So for example, you may have some sort of sequence, particularly for BMS, you may have other logic, but generally a safety system will normally be self-contained. So it would be expected that you'd rarely find additional logic outside of safety logic within the safety controller itself. The idea is a safety controller performs safety functions. You would have a separate process controller to perform process control, and maybe another controller as well to perform process shutdown. But typically process shutdown and process control, they're combined, but you'd have a separate safety controller. Now, because it's a safety controller, PACSystems SafetyNet does have some restrictions. The first is one I've already mentioned. Safety and non-safety functions must be non-interfering, i.e. you don't mix them. So you don't put safety functions in the non-safety controller, because then they will be outside the scope of the safety system. And equally, you don't want your non-safety functions to interfere with the safety function, so you don't put non-safety inside the safety controller. And that's a recognized methodology for doing it. Yes, it puts up the cost of the hardware because you need a safety system as well as a non-safety system. But generally the users of these sorts of systems, they will accept that and they will be happy with the costs. And of course, you're mitigating the safety issues, which we referred to right back at the beginning of the slides. As I say, we only support safety applications. So in the CPS 400, there are a few restrictions. We only support the safety logic and a very limited subset of other logic. For example, C blocks are restricted. You can't use C blocks in a CPS 400, and you can't use Profinet in a CPS 400. Now, there is an option if you wanted to use a CPS 400 as a CPE 400, that is possible. You can put it in non-safety mode, and then these restrictions are removed. But when it's in safety mode, you do have these restrictions enforced. I mentioned PAC Edge is not included. DMP3 is also not included in the CPS 400. And in the SBI, that's for safety bus interface, that does not support any expansion I/O, and that doesn't support any local logic. It's dedicated for being used as a safety bus interface only. Now, there are potentially some advanced diagnostics that you might want to implement in your project. So for heart, If you want HART, you'd have to use an external SIL approved multiplexer, and that would bring out the HART signals to an external system. If you want to do sequence of events, we do have some first up reporting capabilities inside the function blocks, but they're not normally timed. So if you wanted a full SOE system to do sequence of event reporting, then you would have to take your inputs into a separate SOE system, and that could be based on our standard PACSystems controller. Open wire, shorted wire, output feedback, other sorts of diagnostics, they can be implemented, but for that you have to use a suitable field terminal assembly. And if there's any sort of proof testing, that must be performed manually. So typically that would involve some sort of push button, or possibly being done by the HMI SCADA, but bearing in mind what I said before about writing to the PLC, and that would be a manual test that's performed. Currently, we're also not implementing pulse tests, so that's another reason where proof testing comes in. That issue or capability to do a pulse testing to resolve issues, that's not currently supported in our existing VersaMax IO modules. Now, there may be additional restrictions, so you would need to refer to the safety manual, and you'd also need to look at the relevant safety standards. And I do have a safety standards and implementation slide deck that goes into this in a bit more detail, which I can cover as a separate session. And of course, you'd also need to refer to that functional safety assessment. That's the key to what is allowed and what isn't allowed. Just because PACSystems SafetyNet can do something, it might be that that's outlawed or restricted because it's a non-safe application in the overall safety function. So for example, there might be proof tests that have to be performed at particular times. That would have to be implemented as a manual standard operating procedure. It's not something that the system itself can perform. So you often have these other safety functions and safety things going on around the safety system itself. So here's a summary of the PACSystems SafetyNet. It's safety approved to SIL 2 under IEC 61508. So again, note that's hardware approval. The end user or their integrator must integrate and approve under IEC 61511, which means performing that functional safety assessment and following the results of that assessment. The safety manual defines allowable architectures and instructions. Typically what you do is to actually do the SIL calculations. For that, you would use a piece of specialized software, and the reason is that when you're implementing a safety instrumented system, it's the complete system that has to be approved. It's no good just approving the PLC part. You also have to approve the input, the actuator, and the outputs. All of those also need to be safety approved, and in our case, also the field terminal assemblies. So there are software packages available for that. Excellentia is one, and that includes the PFD and the other figures, and that allows you to perform those SIL calculations. And then the output from that can be part of your documentation that your system meets the required safety level. And why is that needed? Well, if anything does go catastrophically wrong, someone is probably going to review what happened. In the UK, that would be the Health and Safety Executive or the HSE, and they would want proof that you performed due diligence and that you made the system as safe as you reasonably could, and that you operated the system in a safe manner. And those calculations are part of that documentation to prove that you did as much as you can to mitigate any safety issues. Now, it's for low demand operation, typically emergency shutdown or fire and gas. Low demand operation is categorized as less than once a year. So as I said, ideally, it's never going to happen. If you do have a fire, well, really, you never want the fire to happen. You don't want to have a leak. You don't want to have the system have to operate. The diagnostic coverage is greater than 60%. That comes into your SIL calculations. And when we talk about system response times, we can get a response time down to about half a second, possibly a bit faster. But a thing about these safety systems is they aren't designed to operate very quickly. If you're talking about machine safety, you might want operation down to 10, 15, 20 milliseconds to stop the operator from being harmed. But with these sorts of safety fit systems, normally you don't want them to operate too quickly. If they operate too quickly, you get spurious shutdowns, which can be very expensive in operational times. But also you do need to establish that there is actually an issue that needs responding against. So if you've got a flame detector it needs to actually detect there is a flame, and a typical response time in my experience is normally around about 5 seconds. So, for example, with a flame detector, that would prevent a spurious reading from, say, a reflection of sunlight coming from, say, when someone opened the window or parked a car in the car park and there was a flash of sunlight which went into the receptor. So typically system response times don't need to be that quick. Equally, they don't have to be that slow either. You don't want to wait minutes. And again, this is where your functional safety assessment will define the effective required response time. Now, I mentioned that network switches are out of the safety system scope, so are power supplies. So you can use any suitable devices. The plan is that the system, if there is any failure, will shut down to a safe state. So you might want to choose components which are more reliable and industrialized than standard components, but we don't actually include those in our safety certificate. Now, as well as the safety certificate and approval to SIL 2, we do have other approvals as well. So there's UL and CE marking. Everything is approved to ATEX Zone 2. We also have NFPA certification. NFPA 72 is for fire and gas in the US. EN 54-2 is the European equivalent for fire and gas systems. And there's also some other NFPA approvals as well for burner management systems. So let's take a look at some architectures. This is a probable minimal system. We have a simplex safety CPU. We've got the PAC channel network, and we've got 2 sets of Versamax safety I/O with the required field terminal assemblies going down to the safety I/O devices. Note on this one, we've only got a single link between the I/O and the CPU. The CPU has 2 ports, so effectively those switches may not be required. So you could do a very small low-cost safety system with a fairly small set of components. I've put here on redundant power supplies, but again, you might not need redundant power supplies. A simplex power supply might work, but of course, from an availability point of view, if a single power supply fails, then the whole system shuts down and your plant trips. So redundant PSUs are not mandatory, but are recommended. HMI SCADA is optional using OPCUA communications. Engineering workstation, that's your PAC Machine Edition software, and there will be an optional interface to DCS using either OPCUA or Modbus TCP communications. Quite straightforward. With that one though, you're limited with Versamax to 8 I/O modules, so that would limit you to how much I/O you could actually have in this system. But for a small system, this would be entirely feasible to implement at a relatively low price. This is more what I expect to see as a standard solution. Now we have 2 safety CPUs with a primary CPU and a backup secondary CPU, synchronized using that LAN 3 with a dual Ethernet network. This time we've also got dual networks down to the I/O and dual networks to the OPCUA communications to HMI SCADA and to the DCS. Note, because we've got dual networks now, we now exceed the capabilities of what the Versamax safety bus interface can achieve. So now we do need those switches. So this is more what I would expect to see as a typical architecture. And this one also gives us the capability of having more I/O, which I'll come on to in the next slide. So here we see the same as before, but now using those switches, we can link with additional network cabling down to additional I/O drops. And by having additional switches, we can also have a distributed system all running off that safety Ethernet network, black channel network, and we can distribute pretty much as far as we like. We are using EGD, which is non-routable, but potentially with a combination of the correct switches and fiber networks, these could be several hundred meters or even kilometers apart from each other. The I/O limitation would be as the SafetyNet system, which is 2000 I/O maximum, or actually that's 1200 analog in, or 2560 digital in and 2560 digital out. That would be quite a large system by safety standards, but that's quite a large system itself. But if you wanted to, you could go to a larger system by having multiple safety systems together. So here's how we combine SafetyNet with process control. We do have that EGD communications, so using that simplex or dual network, we can link to a standard CPU I'm not showing the full network architecture here. There might be additional switches required, but using a standard CPU such as a PACSystems CPE200 with Ethernet global data, then we can have the safety in the safety system inside PACSystems SafetyNet, and we can have the non-safety controls inside a standard PACSystems CPU. Again, we can offer additional hardware around there, switches I mentioned, and also power supplies. Typically, if it's going to be a simplex CPE200, you'd have a simplex power supply for that system, but you may have additional power supplies depending on what the I/O load is and how you want to segregate your inputs and outputs and so on. So that's a system that we might want to use, and if you wanted to implement analog outputs, that's one way we would do it. If you wanted a redundant process control system, we can do that as well. So now we've got our safety solution comprised of PACSystems SafetyNet, and now you were using a redundant PACSystems solution. In this case, I'm showing CPE 400 and CPL 410 in a hot standby arrangement. That could also be a PACSystems RX3i system using RMX redundancy. And now, of course, we have Profinet. We can do a fault-tolerant communications network, non-safety, but fault-tolerant. And now we can do what we want with the I/O. So we can integrate non-safety I/O, including HART. We can also do sequence of event recording. And you would choose what the power supply arrangement is. And again, the network architecture is out of scope of what we're discussing here, but you could use appropriate switches in order to meet whatever your configuration requires. A key point here, and on the previous slide, is your SafetyNet system and your process control system, they're all programmed using that same engineering workstation software, which is PAC Machine Edition. And because we've got OPCUA, you can integrate all of these into the same HMI SCADA solution as well, which of course for us would be Movicon. So I'll just finish up quickly with part numbers. For the safety system, we have the IC695 CPS 400, which is the safety controller without energy pack. The energy pack is optional. And what we do generally for the safety components is we add SN for SafetyNet onto the end of the part number. So you could use IC695 ACC 403 SN if you wanted the energy pack. For the safety bus interface, it's IC200 SBI 001, and you're always going to need at least two of those. The safety bus interface requires a power supply, which is the IC200 PWR002 SN, and then you would have as many IC200 CHS022 SNs, which is your safety chassis, one I/O module for each one. And then you've got the safety I/O, the ALG264 SN, you've got the discrete inputs, MDL650 SN, and your safety discrete output, MDL750 SN. We are planning these field terminal assemblies, but currently they're not in the Emerson price list. That will be a future addition. And on the non-safety side, it's whatever you need. Starting off with an EPX CPE200, whichever one of those you use, and then you could use a combination of whatever RSTI EP or other I/O you need. And here's the same bill of materials, but now on the non-safety side, I've gone to a redundant CPE 400 system. So you probably use the CPK 400 part number, which is the edge controller with energy pack. And in this case, I'm showing RX3i I/O using our IC695 PNS001 Profinet scanner. And I've got HART inputs and outputs. And I've also got the diagnostic I/O there, which give us the greatest capabilities. So that's PACSystems SafetyNet. Fundamentally, it gives us a very comprehensive, scalable, flexible, and easy to use SIL2 safety solution based on the same components that we're using for our existing PACSystems and Versamax ranges. These are mature products, but expected to be continued in use until at least 2035, so they have a long life ahead of them. And a key issue or a key benefit that we have, it's that single programming tool. PAC Machine Edition, the same programming tool you use to program your standard PLC, that's the same one that we also use to program all of our safety and other equipment as well. So machine safety, process safety, VFDs, the programming communications, the Profinet integration, the safety functions, the non-safety functions, all done with that single programming tool. And of course, the other benefit, it's all one Emerson. So as well as providing safety and non-safety, we can also provide all of the other items that come from our Emerson portfolio.